Good morning again, and welcome back from the coffee break. Let me just start by thanking WavEC for organizing this seminar and also for inviting me to be here. It's always a pleasure. Thank you. This session will be about technology, innovation, and research. So we are going to have here a broad range of solutions that are going to be presented by our speakers. I would say that within the marine renewable energies, I would say that different segments of the market are going to be addressed. So it's a very rich panel, and I'm quite enthusiastic actually to be here, and thank you all for being here, because I'm going to skip all the short bio of all of them, but I can assure you that they have a very relevant experience in this area, and knowing that all these people that coming from a lot of well-known companies and have this experience all around the world in this sector, developing new solutions and technologies for marine renewable energies, brings me a lot of enthusiasm and also confidence in the future. I would start with presenting João Neves. He is the Director of Strategy and Business Development from X1 Wind, and is going to present an innovative single-point mooring system to reduce the LCOE of floating offshore wind. João, it's a pleasure. Please.
Thank you very much. Good morning, everyone. Thank you very much for the opportunity to present to you here today. I'm here to talk to you about innovation. Of course, it's the theme of the session, and how our weather vaning system can reduce the LCOE of floating wind. Just before we start, very briefly on the team and where we come from. Our concept was developed back in 2012 by one of our co-founders, Carlos Casanovas, in MIT. He was already an engineer at GE, well, at Alstom, that, as you know, was later bought by GE, and at that time, he already saw that the future was really offshore, and not only offshore, but also floating. So we developed the concept at that time, and then the company was established a few years later with the other co-founder, Alex Raventos, in 2017, and the first patent was established. Since then, we've moved quite quickly in technology development. We've had 3 tank testing campaigns. Also, I will show you in a few slides our prototype in the Canary Islands, and also 3 rounds of investment, the latest of which saw Technip Energies coming in as one of our shareholders, which of course, for us is a very good sign. It's one of the companies worldwide with most experience in EPCI, in oil and gas, also betting now on the energy transition. So it was a great milestone for us. And also very briefly on our team, we are about 35 people now. Most of us with I would say 95% of us with the background in technology, and we bring together two of the disciplines that in our view are the most important for this industry, which is on one side wind, so turbine O&Ms and design of wind turbines. On the other side, the naval architecture and naval engineering. And in our view, this is so important to bring, and it leads me to start a little bit of our technical perspective on floating wind. It's so important to bring this because, of course, floating wind is a nascent industry. The previous session it was mentioned. There's only a few parks installed, the biggest one 50 megawatts in Scotland. So we feel there's still innovation to be brought to the industry, and else that will drive the competitiveness of the industry, of course. And there are technologies that exist, and these are the 3 main ones. You will know them: SPAR, semi-sub, and TLPs. And they work well, especially the 2 ones on the left. They work very well, actually. And that has opened the industry, and that's probably the reason, or one of the main reasons why we are here today. But still, they have problems. And one of the main problems is that they need a lot of weight and a lot of volume to stay stable. That's one of them. And the second one is, as you increase the height of the turbines, as you know, now the industry is talking about 15, 16, even rumors of larger turbines, you have increasingly bending moments at the base of the tower that increase with the cube of the rotor diameter. So this is an exponential problem. It's not something that in our view can be easily solved or can make the industry competitive in the long term. So what Carlos thought at that time in MIT was, let's rethink the system, and let's think it in a way that is more efficient for the environment that we are now in, which is floating, no longer the land. And what he thought, you can see here a brief video, what he thought was to make it with a single point mooring, which is the column, I don't know if there's a pointer, yeah, is this column here. So it's only fixed here on the bottom of the ocean with the TLP, and then the whole structure weather vanes as the wind shift direction. So now you have a passive yaw at that point rather than an active yaw at the nacelle of the turbine. And what this allows you to do is you no longer need a tower. You can have a tripod-like structure that works in tension and compression, and therefore you save steel. At the bottom of the ocean, we have a TLP, as we were just mentioning, with less footprint on the ocean bed and better compatibility with other sea uses like fisheries and so on. And on the turbine side, we are proposing to put it downwind. Of course, this is not new, but it's something that is different than the average of the industry, but it allows us to have longer and lighter blades, especially when you scale up to very large turbines. Also, we are developing a quick connection and disconnection system to allow park operators to bring their platform onto the site with a pre-installed mooring with local vessels, and also to tow it out in case they need to do some major overhauls. So, as a summary, this is what we're proposing. This is a prototype in the Canary Islands that I'll give you more detail from the next slide onwards. But we are proposing a design that is lighter, and therefore you save on CapEx, you save on LCOE. Also easy to install. You can do it locally with local vessels. That is reliable. I mean, we are offshore, and offshore is a tough environment, as most of you know. So the least active systems that we have, the least O&M problems we are likely to have to solve. Also scalable for larger turbines, especially when you scale above 15 megawatts, you avoid your bending moments in the tower, as I was mentioning before. And also with a smaller footprint on the ocean bed. That's something when parks start being deployed with 40, 50, even more of these units, the less footprint you can have on the ocean bed and less impact you can have on the environment. That for us is also something key. This is the project in the Canary Islands. WavEC is a very important member of the consortium. They are developing a very, very relevant and probably some of the most relevant analysis on LCOE and other technical economical aspects. And this was just been deployed a few weeks ago. It's a 1 to 3 scale of a 6 megawatt unit, so already quite a big one. I think in one of the images we have a person and we can compare the scale, but the axis of the Vestas turbine is at 30 meters hub height. Okay. And it's part of a consortium that is sponsored by the European Commission, a 4 million project. I will describe to you the different steps in the rest of the presentation. And also we count with other members in our consortium, not only leading R&D centers such as WavEC, but also leading companies such as EDP, DNVGL, and a few others. Just briefly on how exactly we believe that this is bringing down the LCOE of floating wind. Of course, the biggest component that you see right here is the saving weight and saving steel on the platform, and this is really one of the key aspects that we are proposing in the industry. And then also saving steel and material in the mooring and anchoring by doing a vertical TLP rather than having long catenary lines that extend very broad on the ocean bed. But then also in the assembly and installation by being able to do it with local vessels. So even though it's a TLP, having disconnected the mooring and the platform allows us to have an installation with local vessels, so we no longer have the problem of stability when we are installing the TLP, and therefore we can do it with local vessels, and also decrease of need of O&M costs and OPEX throughout the lifetime of the project. Then, of course, as the industry in general, our goal is to industrialize this and to have modular solutions for each one of the elements. So bringing these economies of scale will also bring down the cost and the LCOE. And finally, in the end of the day, it's reducing risk. And this is what the market is looking for. As less risk we have, the less cost of financing also will have in the long term. So we believe that this is a path that not only us, but many in this industry are trying to achieve, and of course several innovations will appear in different places that will allow the cost and the competitiveness of floating offshore wind to increase versus other technologies, and not only versus conventional fossil fuel technologies, but even versus other renewable technologies. I will spend a few minutes on the slides of the actual project, the actual Pivot Boy project, because it's the core of the innovation that we bring. The process started in 2019 with the design and tank testing, as I was mentioning in the beginning. Then we did a few modeling campaigns with OrcaFlex and Dock2 with the Technical University of Denmark, and also some CFD campaigns with Fraunhofer Institute in Germany. And in this case, just a quick note, because it's we find this quite interesting, quite important. We did this one because the traditional response that we get when we talk about downwind turbines is really this tower shadow effect, which was the reason why onshore wind always went upwind, because we have a very big tower that can produce a shadow effect. And we wanted to confirm if that was or was not the case in our structure. And as you can see in this brief CFD scheme done by Fraunhofer, the steel elements are so thin that the flow of air recovers very easily before hitting the blades of the turbine. So by having this type of tripod structure with thinner elements, we solve this tower shadow effect that has haunted the onshore wind industry for some years. Then after we finished the design stage, we started manufacturing in the north of Spain. So this was manufacturing in Santander, in a steel manufacturing workshop in Santander. In different places, was shipped to the Canary Islands. We assembled it in a shipyard in the Canary Islands with local cranes and local means. We of course assembled also the nacelle. We bought this nacelle from Vestas, and then after the loadout, we did the rotor assembly and all the tests that are associated. And then, of course, we put down the foundations. There are three concrete blocks, reinforced concrete, also produced locally in the Canary Islands that were put with normal tugs in its final location. We installed the cable in June this year, I believe. A 20 kV cable that is connected to Plocan smart grid. So it is the prototype is installed in the Plocan test site. And then we did 3 weeks ago, I believe, the final installation also with local vessels, which is part of this stable platform. Even though being a TLP, being stable allows us to do this type of installation with local vessels, increasing a lot the fleet that you can use in this type of projects and decreasing the cost. At the same time, of course, the industry is moving, and we've heard in the previous session that developers are thinking big, and we're happy that they are thinking big because the planet needs it. So not only we are doing the small, this is the one that you just saw in the Canary Islands, the one on the left, and that was already big in the photos, but then when you look at the scale of the industry, in our view, it's really amazing what can be done offshore. So we are developing what we call the X90, so 90 meters hub height, 6 to 8 megawatt of turbine capacity, and then also what we call the X150, the 15 megawatt scale, so 12 to 16 megawatt machine to harbor the largest turbines that have been announced. Not many, well, not any still in serial production, but the big OEMs are developing the prototypes and testing the prototypes, and therefore we are also developing from our side the concept so we can assess its competitiveness in the industry with these turbines. And then finally, just a little bit on the path. So we've validated in lab quite extensively. We are now receiving data from the Pivot Buoy project in the Canary Islands and validating the technology in a real environment out there in the ocean in the Canaries. And now our phase 3, we believe it's important at the same time as the industry develops the commercial 500 megawatts, 1 gigawatts that will be in the water at the end of the decade. And this will take time to develop. So this will take 6, 7, 8 years to be in the water realistically, at least in our view. And we believe that we can still take that window of opportunity to develop what we call pre-commercial. And there's a few of them already. And the advantage of this is not only to test technology, of course that's from our side, but also from the industry side to test supply chains, to test how to put these things in the water, how to have the T&I processes. All of these, there's very few knowledge in the industry yet, and we believe it's important to test them in parallel with the development of the large commercial projects. And just in that view, our pre-commercial unit, let's call it this way, or at least the first one, will be a 6 megawatt unit in the Mediterranean Sea, so in the south of France. We were recently awarded by the European Commission with a big consortium of international companies, and we will be working on this next full project next. So very happy to have this support from the European Commission, and of course from also other public institutions and private companies, and we believe that this is really essential for the innovation component that this industry needs to go through. Thank you very much. It was a pleasure, and I hope to see you soon. Thank you.
Thank you, João, and thank you for also be strict with the time. We will keep with the presentations, and at the end you will have the possibility to put some questions to the speakers. Next speaker is David Carrascosa. Please, is the Director of Operations of SAITEC Offshore Technologies, and is going to present us concrete floating wind from demonstration to large scale. Please.
Okay, thank you very much. Thank you very much also for the opportunity to present here such a nice audience, such a nice framework also as presented before. And yeah, I'm going to speak a bit about concrete. We've seen steel solution before. By the way, I told you congratulations on the milestone, João, installing a floating offshore wind turbines is what we need for the industry to move ahead, right? So I'll speak a bit about what are we doing in this field. SAITEC Offshore Technologies is a spin-off from a bigger company, bigger group. That's the SAITEC group, multidisciplinary and global engineering services company with headquarters in Spain, but again an international vision and a huge commitment to innovation. And proof of that is actually the launch of this spin-off, SAITEC Offshore Technologies, which is the company, the business unit we have to focus on floating offshore wind. We are now more than 40 people, fully focused on so let's say full-time employees for floating offshore wind, and obviously we gain the support from the mother company. But we have let's say as well we have this heritage of this global ambition, and that's why we've been doing prototypes, and we are doing prototypes in Spain, but at the same time we are involved in projects in France, in Scotland. We have a project being developed in California, our first subsidiary in Tokyo in Japan, and we are also developing projects in Australia. I could speak about the process we've been doing so far for the last 10 years, which is more or less the time we've been developing the patents, the models, and so on. But I prefer to focus on what's, let's say, the latest milestones we've achieved in the development of the SAF technology, which is this concrete barge we have developed in SAITEC. And that, let's say, latest milestone is the DemoSAF construction and float off. DemoSAF is a project that is using a 2 megawatt wind turbine. It's a project that will install the first floating offshore wind platform connected to the national grid, so providing electricity from a floating wind turbine to the population in Spain. And it's a project in partnership with RWE. RWE, I guess most of you know the company, is the second player worldwide in terms of offshore wind assets. So a great companion for this project. The DemoSAF project, I mean, the location for the DemoSAF project is BIMEP. BIMEP is a test center, which is co-funded by the regional EBE, which is the energy association, so the energy agency for the Basque region, but also from IDAE. We had Carmen before speaking on behalf of IDAE. So it's a public infrastructure which is not that well known sometimes, and it's there to provide submarine cable already laid for the installation of these kind of devices. Concrete, right? So I said it's concrete, and what does concrete provide? Well, on one hand, it provides competitive cost, reliability in terms of the supply, and also a price, let's say a raw material price which is stable, and also the capability to perform local projects. The good example is the DemoSAF project. More than 75% of the construction budget has been awarded to companies headquartered 25 kilometers around the port of Bilbao, where the platform has been built. So following that initial slide, I thought it would be good to go through a bit of the project itself, which started by onshore construction there in the port of Bilbao. as I'm going to present afterwards, the construction has been inspired in what the industrial production will be afterwards, and that's been like, yeah, the way we've thought about the whole project, not being a project with the only and sole objective to test our device in the water, but also to try and test the whole process, and that's, yeah, how the project and the construction process was engineered. So we divided the platform into several pieces, and then we assembled them all together as if it was a puzzle, and that also proved the capability we have for precast of the different pieces of the platform, and then the installation. We performed in summer as well the installation of the mooring system. It's already, yeah, sizable. It's a 2 megawatt turbine, and yeah, sizes as you can see are pretty relevant. The hub height for the platform is 70 meters above seawater level. We are using, yeah, kind of the suppliers that would probably be involved in commercial platforms and commercial wind farms. And that's very good, because we've been also, as a company, been playing the role of full EPCI. So we've been placing the contracts for all the single supplier in this project, and we've been learning quite a lot, right? So RWE has been always there assessing and advising, but really SAITEC is where the company that's been leading on all the contracting and yeah, the management of all the operations. And yes, one of the latest operations we did was the float off. It's interesting to see that it's one of the very few multi-megawatt platforms or multi-megawatt demonstrators that has been fully assembled onshore. So both the platform, tower and turbine have been assembled onshore, and the whole system is actually the unit that is being performing the float off operation. So yeah, obviously kind of a set of milestones, very, very important. It's obviously not the last step, and now for, let's say, the following slides, I'm going to go through a bit, yeah, what do we have in mind after the DemoSat project, which, yeah, is providing good learnings, not only in the technical background, but also in terms of legal, contracting, stakeholder engagement. When yeah, projects get to this size, even if it's not a wind farm, you still need to go through a stakeholder engagement process. So yeah, that was an interesting milestone. But as said, yeah, what's next? And I've got a slide which I think provides a bit of a feeling. If we focus a bit in Iberia, we see there is potential, but we see also on the right hand side, yeah, what's the lack of continental shelf we have, right? So it's obvious we need to go for floating, and I think it was a bit of a representative figure to see, okay, there is resource, but there is this lack of continental shelf, so floating offshore wind in our region is a must. In that regard, we are obviously linked and we are involved in commercial developments, as I said before, but we are also taking a step forward in terms of having wind farms ready in the midterm. So not let's say not waiting for the full commercial development. We feel like it's very important also to take an intermediate step, and that's pre-commercial wind farms. I think João, you also mentioned that 50 megawatt is a sizable size. It's a sizable project. It's also kind of in this medium term, which will provide the opportunity to the key stakeholders to understand what is floating wind and not not knowing what is it once the commercial projects are announced. Everyone is scared about what floating wind can provide. Same thing we are doing in the US in collaboration with Floventis, and that's the Cademo project where SAITEC is one of the technologies selected for the project, which will be a 60 megawatt water project in the state waters. And then finally, everything feeds into the industrial production. So as I said before, the entire demosat was intended to be also a test bench for what we will be using in industrial production. We are doing great advancements in how to shape the production and the serial production of this unit, with the objective of being able from a single plant to produce 1 gigawatt a year. That's obviously not something that will happen tomorrow, but through learning curves and different phases into the industrial constructions, that's what we want to aim. And then as a final and last slide, sizes are we all speak about the lack of infrastructure, the sizes of these elements, and I think it's always good to make a reference to let's say a structure we may know. We've seen several wind turbines compared to the Tour Eiffel. We come from Bilbao, and then we do the comparison differently. So that's the comparison of a 12 to 15 megawatt platform compared to the football stadium of the Athletic de Bilbao. That's the Sathletic name coming from. And that's the kind of things we are going to deal with. And 1 gigawatt a year using 20 megawatt turbines will mean 50 of these units a year. So almost one platform to be delivered a week. If we see the figures, it's thousands and thousands of turbines. So I'm very, very willing to enter into the discussion afterwards. Thank you very much.
Thank you very much, David. Now we will have Alex Fairtlough, please. He comes from EnerOcean and is going to present W2 Power, sea-proven technology for cost-effective floating wind power now. Please, Alex.
Good morning, ladies and gentlemen. It's a pleasure to be here, first of all, in this beautiful Museo de Oriente, and I thank WavEC and the Spanish Embassy for inviting us to this exciting panel. It's been very exciting indeed up until now. EnerOcean is actually the oldest, it's a small company, but it's the oldest marine energy company in Spain, and has been developing the W2 Power, floating wind power platform that you see here, since 2009. I'll start with a short video. Here. As you see, W2 Power is a twin turbine concept with inclined towers. The system is moored here at the front column that you see here, and it's moored. It has a rotational swivel system in the front column, which allows for the whole platform to rotate and to align with the wind naturally, let's say. And here you can see when it was installed at sea, the mooring system is very simple. It's in this case it was a hybrid mooring, and it took 4 hours from the moment we took it to sea to connect it and to get the turbine started. Yeah? It was a very successful, as you can see, it was a beautiful day. It was a very successful installation, and we had no problems at all. The platform was towed out with a single tugboat, which is what would happen with the full scale. This is a 1:6 scale prototype, which is still sizable, with the nacelles being installed at 15 meters above the sea level. This is actually in the Plocan test center, which is just off Gran Canaria. The results, it was out at sea for 4 months. All the manufacturing and installation methods were validated. As I said, the mooring was very simple, and also the decommissioning, the removal and bringing it back to port was very simple as well. The passive alignment worked beautifully, It aligned even with moderate winds, and was actually the misalignments that we saw were actually less than the thresholds you see, which activate yaw mechanisms on standard turbines. So we validated the subsystems, the mooring system. Also, it had advanced monitoring systems with a communication to land, which all worked perfectly. Stability and reliability was demonstrated. We never had to go to emergency mode. We never had to access the platform for maintenance during the 4 months. And we faced really severe conditions. I mean, there were 7 storms with 4-meter waves, which don't seem much for a normal platform, but this was a scale 1 to 6. So these are 24-meter equivalent waves. And one wave was actually bigger than 30 meters, which is equivalent to the one here in Nazaré, which is very famous. So if you ever go and see that, you can just imagine being hit by that, and the platform withstood that quite comfortably. As you can see here, we collected lots of valuable real-time data. At the bottom, you see one of these waves at 24 meters hitting the platform, and basically the platform is very transparent, and it just runs through the platform. That's over a 4-meter wave, and the platform hardly moves. And at the top, you can see, you have to look at the horizon. There is movement, of course. This isn't a full storm, but it remains within the tolerances that wind turbine manufacturers require. So we were very happy with these results. Okay, this was all done. We're here talking about innovation. This is a long process from 2009, from the first idea. As you see, the towers were vertical, but then we saw optimization was achieved by inclining the towers to maintain the distance between the turbines. And then obviously we saw this was very effective. We patented the idea immediately, and the patent is granted. And we then went through all the testing that needed to be done through the TRLs. All of this was done with support of European and Spanish institutions, which was valuable support, but also under their scrutiny. Yeah, so we had to be checked carefully, and we passed all controls admirably, and we went through to, this brought us to the test that we just saw in the video on the TRL-6. So what are the advantages? We said the lightweight, it's got a very low draft, it's very important, and the optimization of steel. We believe we have the lowest steel per megawatt of any concept out there now. The turbines, having 2 turbines, okay, it's good to go big. You want as much power per platform. But if you go for a big turbine, obviously you have to install at heights, as we said, of Eiffel Tower heights. I mean, you need cranes to get up there, yeah? And so by putting 2 smaller turbines, which are now in the market, they're proven reliable turbines of 5-6 megawatts, you can achieve 12 megawatts without having to rely on this expensive infrastructure, the advanced vessels, and also for maintenance. You have easier access. The self-orientation system allows us to not rely on expensive yaw mechanisms and the ESATI Engineering Solutions. This is actually my company. I'm an investor too in EnerOcean, and we've been supporting wind turbine OEMs for over 15 years, and we're bringing our experience into designing the towers, these inclined innovative towers, and also integrating the wind turbines. What's next then? Okay, we're also step-by-step company. Next step is an experimental farm, so we're looking at a farm of 48 megawatts. And then we'll be looking at the first commercial wind farms and looking to go fully commercial in 2026. And we're looking at a 1 gigawatt pipeline before 2030. You can say that's ambitious, but with Eni with us now, we can see this as something which is obtainable. And here we have 2 farms that we're focusing our efforts on, which are just off Gran Canaria again, Canary 1 and 2, and we're already advancing with the environmental studies, and we're waiting for the Spanish government to present the permit plan so that we can go to the next steps. So thank you very much for your attention. Obrigado.
Thank you very much, Alex. The next speaker is Misael Goicoechea. I think I pronounced it correctly. He's from ACCIONA Construcción. and he's going to present us the serial manufacturing of concrete foundations, a roadmap for scalability of offshore wind.
Yes.
Please, Misael.
So we've been talking about how the market is going to bigger turbines, wind turbines, and there's a certain goal for scalability. But when we think about scalability, it's not just about finding solving the technical challenge of taking higher loads. It's also an increase in dimensions. It's an increase on the requirements for the supply chain. It's an increase in the whole process chain of value of offshore wind. From our experience, we have experience with the manufacturing of concrete foundations, and we find that our solutions for manufacturing might be the key to scalability, to finally policing those aspects of manufacturing, of transportation that might be challenges when we go to even bigger and bigger wind turbines. So let me quickly talk about how ACCIONA went into this venture. We consider ourselves at ACCIONA as a global provider of sustainable solutions. We have solutions for the market, energy market, infrastructure, waters, cities. And we are a global company with presence over 40 countries and a long history. We have more than 100 years of history, and we are focused. We've worked a lot in Spain, in the Iberian Peninsula. And one of the main commitments of ACCIONA is sustainability. And this has started really early through our sustainable master plans. And we can proudly say that we are carbon neutral since 2016. So we're trying to promote that sustainability even from ourselves. We have really good consideration in the global sustainability indexes as well. And also another important aspect is that in this 100 years of history, we have developed strong and really, we have evolved that know-how into the building of maritime structures. We focus on the construction of maritime concrete structures, and we have designed and executed over 60 ports. We have more than 14 kilometers of breakwaters, as well as quays and piers. This synergizes this knowledge about how to manufacture concrete structures for the maritime environment, and this commitment for sustainability have a perfect synergy into developing a portfolio of offshore wind solutions. These are our portfolio of offshore wind solutions that we try to cover the whole depth, the whole technical challenge, from fixed solutions with a gravity-based technology to the semi-submersible technology, and probably our most innovative concept, the tension leg platform made out of concrete. To go quickly about all these designs, the Argo, which is our name for the concrete ground-based solution, it covers a depth up to 50 meters. It's manufactured in a conventional caisson construction through slip forming, and we have designed this turbine to withhold 50 megawatts turbines and the loads of 50 megawatts turbines. One of the key aspects we focus is that within the whole chain of operations of a turbine, we have transport, we have manufacturing, we have the commissioning, we thought that one of the main challenges for gravity-based solutions was stability. So this solution is self-stable. This allows us to do wet storage, to optimize the stages of manufacturing where we're stowing just and getting ready the platform to transfer it to the site. And it also means that, for example, this platform is self-installable up to 30 meters. Going to our floating solutions, which are probably more innovative, we have a semi-submersible concept with 4 concrete columns, vertical, simple structures, and we will see this in simplicity is the main advantages. It uses conventional mooring line, chain mooring line anchor systems, and it's a really robust solution for different sites and different conditions. And probably our most innovative solution is the TLP CT-BOS, which is a concrete TLP which has been designed for 15 megawatt solutions. Both designs, the semi-submersible S-BOS and the TLP, have been tested in a scale model in a towing tank. And the main innovativeness of this concept is that this platform is stable, so we avoid one of the biggest problems with TLP might face, which is transport, needing barges, needing heavy lift equipment to be able to transport unstable platforms to site. This design is stable by itself, so we can use conventional wet towing with a tugboat and anchor handling vessel to transport this solution, which really offers a competitive, or brings a lot of competitiveness to this design. But what do these three designs have in common? Well, these three designs have been designed to be manufactured through slip forming, in using our knowledge about port infrastructure construction in concrete, so floating docks. And we have two main ways of building, and one is in an assembly line, just like a car, moving through different stages and evolving the platform. This means that we can accelerate our production rates, which is also a requirement for scalability. Up to one of these lines, we estimated that can produce up to 800 megawatts yearly. So foundations for turbines with a park of a site with that capacity. And it was mentioned previously as one challenge, the space in ports. And then we have the floating dock manufacturing line, which allows us to reduce the time for float-offs because we are already building in water, and to even improve the speed of our production line. Another main aspect that was mentioned is that because we're building in concrete, we find that this technology is easily exportable to different locations. And we can bring this solution to wherever, as close as possible to the site, as long as there is port facilities close by. And we offer local content there. So it can be installed wherever, and we can install this manufacturing line. It's not as a specialized technology that has to be developed in one singular spot. We have we have manufactured caissons in Senegal and many other countries, bringing that technology there and using their supply chain and giving 100% local content to that aspect. Another advantage of this flexibility is that we can also reduce transport times, because we are reducing the distance that has to be traveled with the platform. So, So what are our next steps? Well, we have our concept defined. We performed feasibility studies. We have tested this. Give me a second. We have tested in Tomatank the platforms. This is the city bus being tested in a model scale. We found really good results, and they're leading to decreases in the weights of the structure, because we found that they could be optimized. And our next step is to prove this technology, not to only prove the TLP concept, which is quite innovative, but also prove that this manufacturing system can be used for floating wind and to accelerate the production rates we will have in the future. In order to do this, we have this European proposal, this project, where we're a consortium of really knowledgeable partners for the construction of over 8 megawatts real scale demonstrator for deep waters. This project is starting right now, and it's starting with the selection of a test site, and we studied different options for the test site, and we found that Viana do Castelo is probably probably not absolutely the best choice, because we find that the meteorological conditions here are strong, and that's the perfect opportunity to demonstrate it. That's what we're doing, demonstrating. So we're going big with a big turbine. We're going to harsh conditions to demonstrate that our concept is robust. We don't need more benign weather conditions. This is a technology that is robust, that is able to be installed in harsh conditions and work there. And we also find that there is an untapped potential in the Iberian Peninsula for floating wind. And by installing this solution in Viana do Castelo, we might spearhead and push a little bit more towards the development of floating wind in the Iberian Peninsula. Thank you.
Thank you very much, Misael. Our next speaker, Lúcio Rodrigues, is Head of Procurement and Project Support at Principal Power, and is going to present us WindFloat, ready to bring floating offshore wind forward onto utility scale in Iberia.
Hi everyone. Very pleased to be here and to be participating in this seminar. So the objective of this presentation basically is to show everyone that we are ready. So we don't have any further development apart the commercial projects. Through the slide you're going to see what we have done to arrive to that stage. But I wanted to give a bit of context. So what we are seeing today, if we want to keep the goal of having net zero emissions by 2050, that means that, and to keep the 1.5 Celsius degrees of pathway, that means that we need to ramp up the current deployments of offshore wind. So here you can see what is the cumulative onshore and offshore wind, and what we can see is that we need to ramp up urgently so that by 2013 we would have 270 gigawatts of offshore wind, and that means that we need to ramp up from 6 gigawatts per year to 80 gigawatts per year till 2013. So, and that shows that there is a huge importance of the offshore wind, and in particular, and considering what we can see here, that 80% of the offshore wind resources are placed in waters deeper than 40 meters. The floating wind shows that it's quite competitive in order to tap the energy production that we can have in those waters. So just talking a bit about Principal Power. Principal Power is a fairly new company that was founded in 2007, is based in California, but we are also present in other 4 countries. So basically we are present in Portugal, France, Japan and the UK. We, as you can see here in the picture, we have tried to segmentate the different promising markets. Hopefully in the future we will see more green markets and less or yellow or less gray, but this is what we are seeing today. Talking a bit about our design, basically the WindFloat is 3-column semi-submersible that on the bottom of each column has what we have called the water entrapment plate, that I'm going to speak a bit more afterwards. The columns are connected through main beams, upper main beams and lower main beams, and the trusses. And then there is the catenary as a mooring system and the inter-array cable. Moving a bit more and talking a bit more in detail about the main features of the WindFloat. So the first one that we like to mention is the fact that we are quite turbine agnostic. So we are not connected to any wind turbine manufacturer, and we believe that that's important. Of course, we need to work with the different turbine manufacturers in order to adapt the design to the specificities of the manufacturer, but we are able to do that. The other feature that we have created is the damping plates. We call it water entrapment plates. So the water entrapment plates allow the WindFloat to have better behavior in terms of water-induced motions. Another system that we have working inside of the platform is the smart hole trim system that basically displaces water inside of the 3 columns, that allows the WindFloat to have an even keel behavior. So in that way we intend to improve the energy production of the wind turbine. And finally, the passive ballast system, which allows us to play a bit with the operational draft, but also to adapt to the project execution plans in terms of ports and shipyard or fabrication areas. So, and talking about the projects that are using currently the technology that Principal Power has developed. So here in the video you can see, this is a real video by the way, here in the video you can see the wind float Atlantic that everyone I believe already knows. So basically the first production was in 2019, is located 20 kilometers off the coast of Viana do Castelo. The water depths are about 100 meters. It holds 3 Vestas wind turbine generators of 8.33, and it was the first bank-financed floating wind farm in the world. So, in the production that we have estimated so far is about 122 gigawatts hour. Moving to another project that also uses the wind float technology is Kincardine, that has about it has 5 wind floats. Each wind float has 1 wind turbine generators of 9.5. Before the deployment of this project, it was tested the first phase, which was just a prototype. The same prototype that was here in Portugal was placed in Scotland in order to understand how the prototype would behave. And with that, we moved to the phase 2, which was the starting of the project of Kincardine. And the first power production was in 2021, and the production that we estimate is about 130 gigawatts hour. As you can see over there as well, it's mentioned what was the maximum wave height that we have, that the design and the wind floats have faced so far, which we understand is quite considerable, and the production remained the same. Talking a bit more about why we understand that we are ready for utility scale. First is basically it's quite linked to the 2 projects that we have mentioned, that I've mentioned before. So we are retrieving all that operational data and we are implementing into our design loop so that we are fine-tuning the process, and that we understand is quite important. The other thing, and especially considering that the project execution plans of the different sponsors are quite challenging, and that means that we need to have a continuous engagement with the manufacturers, with the fabricators, with the supply chain, so that we can understand, test the supply chain, understand their needs, and with that also improve our design and try to work together to find solutions that we could comply with the schedules and the project execution plans. We have also a comprehensive understanding, considering the different projects that we are involved, of the logisticals and infrastructure bottlenecks, and that we find it important also for the design loop. And finally, we have a quite vast design library that can allow us to change our concept in order to adapt to the project execution plan requirements. So we can say the fabrication schedule, water quayside water depth, and the fabrication facilities. So we try to adapt our design into that. Going a bit more in detail for what we have seen so far in terms of Iberia and the floating wind landscape. So in doing a bit, putting the 2 countries here alongside, so what we can see from the pictures is that both countries are they have a huge potential for what regards offshore wind, and that is also demonstrated from different sources. As it was already mentioned, the bathymetry is quite favorable for floating wind, and that is the same for both countries. In terms of regulatory and policy, The goals are quite high, and today we have seen that the policymakers are setting out these goals, and they want these goals to be achieved. Of course, Principal Power is working in that, and is working to try to achieve those. And in terms of supply chain, the supply chain here in Portugal, we know that exists, but it still needs to be further tested. In Spain, we have seen, and considering the projects that we have been involved, we have seen that they also have the capability, and they are also have been quite involved in the previous fabrication of the wind floats. In terms of T&I, we understand that the vessels needed for the installation of the wind float are quite available in the European market, and so it's not a huge constraint to find companies and means to do the installation. On the other hand, in terms of grid systems, we understand that both countries will need to improve a bit the grid systems in order to handle the increased amount of renewable production electricity. I'm just finalizing, but just to show a bit what we have seen in terms of supply chain from the two projects that currently are in the water. Here you can see in the dark green and light green the different main equipment and main parts that were manufactured and built in the Iberia Peninsula. So what we want to show with this is that this is quite balanced, and we can show with this also that there is a huge potential for the supply chain in Iberia to take advantage of their position and to work as a worldwide player for this market. So finally, and from the picture that you can see here, those are all the projects that we have mapped in the peninsula, in the Iberian market. In yellow, you can see the wind float Atlantic, but hopefully in the future we will see much more. And with that, what we want to say is that the wind float is already proven technology, is ready for the utility scale. That the fact that we have already operational projects in the waters allows us to have a competitive advantage in terms that we retrieve that data and we improve the design that we have. We have already tested the supply chain, the Iberian supply chain, in terms of fabrication, in terms of supplying of the equipment. Likewise we did with the different infrastructure ports and remaining areas that need to support this industry. Thank you very much about that.
Thank you. Our next speaker, Miguel Silva, Managing Director at Corpower Ocean, and he's going to present us wave power to power the planet.
So, good morning to everybody. First, let me take the chance to thank WavEC and the Embassy of Spain, especially Professor Sarmento, because he has been a key enabler of wave energy in Portugal, and wish Marco my best wishes, and from our company, close cooperation will always happen in the near future and the long future if God intends to. So before anything else, I'm not talking about floating wind, as you can imagine. I'm trying to keep the wave in WavEC so it doesn't go away. We still have wave power. So let's speak about our project. That's iWave 5. That's the last two stages of our development. And we'll take a look at the status of the project and the next steps that we're going to give. Important is to think that we have a huge source of renewable energy that's completely untapped. So we take care of solar, we take care of wind, but we didn't take care of wave. Tidal is very well taken care of, but as you know, the resource is lower than the actual wave energy. So we have the same challenge as many other companies that try to go to sea. We have to survive the storms and we have to maximize our revenue to cost. And this has been one of the two main objectives of the project and the development process that is now over 10 years. That's to find a way that we can survive the storms as wind turbines survive harsh winds with the pitching of the blades. And of course, LCOE has been one of our major design drivers. So the product is designed for LCOE from the start and to survive the waves. So that's the bad waves from the sea. Let's keep the good ones. And the challenge that we addressed has these two main drivers, and we think we solved it. So what you see here is an animation of the way our device is working. We have been developing and manufacturing the real scale device. So we've gone from half scale with huge success in Orkney in Scotland to build the first one at real scale here in Portugal and in Sweden. And after this one will follow 3 more devices to install capacity of 1.2 megawatts at the Aguçadora test site. So here's the system that provides us the safety that we are speaking about and the way that we can survive the waves. So we have what we call the detuned state, where the device will not interact with the waves and behaves like a rock. So the waves will pass through the device without interfering with it, and thus without removing the power from it. Maximize revenue to cost. Will allow us, with this wave spring system that you are seeing these black cylinders, to amplify a wave that's of 1 meter up to 3 meters, allowing us to have a very stable production process. These two wave springs, as we call them, are also the main locking mechanism that will put our device into safety mode, similar to the pitch of the blades. This is what we envision for the future. So 4 key takeaways. So we have survivability, as I told you, with this our detuned state where we don't interact with the waves. We phase out of the waves phase, natural phase. And as we get into phase with the wave, production starts to increase very linearly and very interestingly. So we have more efficiency because we use light materials. The hull that you are seeing there, and you'll see a little bit further down in the presentation, is made out of composite, no steel. Only on the main mechanical parts we are using steel, and we are trying, for example, to replace our main pre-tension cylinder, that big white cylinder, with a composite solution that we are developing on another project together with EE Grants and partners in Norway. And of course, we have now 4 times more energy output compared to any other device in our wave energy field. So we have thought, as I told you before, as using LCOE as one of our main design drivers. So we have low capex operations and an high average output because of this boosting system that our Wave Boost can provide us. So we are talking about an installation that only takes tugs into consideration and local tugs. It's a 2-vessel operation and can be installed and retrieved in less than 1 hour, thanks to our Quick Connect system. Of course, what we bring into the energy mix, it's a very stable profile, very base-loaded profile, as we'll see in the slide later on, without the variability of wind and solar. Actually, the profile is kind of complementary to both of those profiles. So what we offer is the way that we introduce a base load profile into an renewable energy mix that has inherent variability. So we, as a company, we are now 75 persons from 14 different countries working together. And the stage that we are now is stage 4 and 5. For stage 4, we are launching the C4, hopefully by end of the month, if the weather window allows it. And on stage 5, and up to 2025, we'll test our pilot array that includes 3 more devices, what we call the 5th generation, the C5s, together with a collection hub that's like a multi-plug, let's say, device where you can plug many wave devices, but also other technologies that then it's plugged to the main export cable. So we have smaller jumpers between devices, and then the concentrator is connected to the main export cable available at the location. So a summary of the device. So it's a rigid connection from bottom to top. We have already installed at the Aguçadora, as we'll see also in the next slide, the anchor that you see there in the bottom, and also the export cable. And after the anchor, you can see what we call a tidal regulator, and then a flexible composite rod that connects to the 4 mooring rods coming out of the device. So it's a rigid connection all the way, and a single point absorber as a class of equipment. And as you see, there is no catenaries, no other solution than a 18-meter anchor that's just vibrated very easily into the ground. So it's an innovative anchor that I can show you there, designed for upward loads, just the opposite of the normal monopile solution. So the sweet spot is after 40 meters, so it matches our bathymetry. We can actually install it next to wind float at more than 100 meters. Each device of the C4 generation is able to produce 300 kilowatts with a very interesting capacity factor already, and will work between 0.25 to 8 meter wave, not beyond that. After that, we'll become silent, and the waves just pass through and we don't interact with them. So what we are doing here in Portugal, lots of things. So we have established our base in Viana do Castelo, where we have our offices and also our research and development building. In that building, we have developed the complete solution, technical and production solution for the composite hulls and all the composite parts that we use, using local brains, because Viana do Castelo is very rich on composite and polymer engineers coming from University of Minho, but mainly for the industry there, from rotor blades to shipbuilding to other auto parts manufacturers. So there's good base of engineering for composites there. And we plan to install the 4 devices that will go up to 1.2 megawatts, plus the concentration hub that you see there in Aguçadora up to the end of 2025. So C4 is on the way. We're waiting for the weather window, and next we'll go for the C5, the next generation of our product. So this is our base of operations in Viana. This is a very small building where we do our research and development in composites, but also the integration of all the parts that are a part of our device. So for that, we have developed this very special concept of a mobile factory that can be fitted inside 2 maritime containers, and it's able to wind the hull, as you see there, at customer sites. So it's a huge sphere-like structure of 9 meters in diameter and 12 in height, let's say it like this. And it's not logistically wise to transport air across the globe, so it makes sense to build the hulls next to the project. So we need a small working cell, as you see there, with temperature and humidity controlled, and environmental equipment, as you can imagine, so we can release good air to the atmosphere. And we wind in a single shot the complete hull without any bonding, without any seams or flanges or joints. So it's a sandwich construction, and it's very hard to find something like it. Fully developed and manufactured in Portugal. In parallel, our colleagues in Sweden have been working on the power takeoff in Stockholm. Here we established the world's biggest test facility for wave energy. We have been operating 2 wave rider buoys in Aguçadora from where we collected the data, and we uploaded to our simulation models. And during a year, our device was experiencing the waves from Aguçadora in Stockholm. So all the loads and all the load cases were tested for a year, and what we call the Ironman test, to prove the concept from PTC, not only that it will take the loads, but also that it will generate the power that we promise that it will generate. So it's designed for smart logistics. We can ship it across the globe on a normal ferry, as you see there. It's coming to Leixões. And in Portugal, inside that building, we have done the integration of both components with integrating the composite hull with the power takeoff that you see there. It's an operation that's done over a few hours and not a very complicated operation. So here you can see the main components. Only the tidal regulator is missing because it's behind the camera. It has a couple of secrets still. So it's a little bit behind the camera. All the other stuff is just composite work. No. And it's very important for us, and the impact on LCOE from composites, replacing steel by composites is great, and this is one of the drivers that led us to choose composite instead of steel. Yeah, the other part of the project that's quite interesting is the UMAC anchor that's developed over a €4 million project and is designed for being easily installed and retrieved. As I said, with vibration, there are several patents on this. It's still not public because we want to do the test with the device, and it's already installed at the Goicoechea, in the Goicoechea. And we are waiting for the actual device to suffer the pains of being at sea to prove that the anchor will perform as it did at Fraunhofer and as it did in São Jacinto in a very hidden test site. So I think as soon as we prove it at sea with the loads from our device, it will be a spin-off from all this project. This anchor will be available for other applications. Okay? So I think it could be interesting for floating wind and other technologies. The anchor is designed for sand, and also for sand mixed with clay. So it's very interesting, I think. So meanwhile, we installed our export cable in the Goicoechea, 6 kilometers of cable, and it's fully connected now with the junction box at the bottom of the ocean to the substation. Yeah, so the future is to have these wave clusters of 10 to 20 megawatts hybridized with wind or not. But we would like to take advantage of the space that's already occupied by wind to introduce a couple of megawatts of wave. We just need 150 meters between devices, and you can see the grid architecture at the bottom of the ocean is not so complicated. So this is what we call a core pack, a 10 megawatt package. This allows us to have a cheap O&M operation. So if you have a spare buoy at your facilities, you just remove one, install one, remove one, install one, and you have maintenance cycles very well under control with 2 tugs. So it couldn't be easier and cheaper to do this. From our plan and calculations, we aim to leave 60 to 70% of all investment in CapEx and OpEx locally. So what you see here and with what we call the wet kit, everything that is in contact with water has been manufactured here in Portugal in the metal mechanic industry, and the composites manufactured by our own company, of course. But the wet kit, it's even the anchor was manufactured in Portugal in 2 different suppliers, so they don't get the knowledge of the complete system. And so plus the OpEx, we are willing to spend between 60 to 70% of the complete project investment locally. Okay, so most likely we have 4 locations in the world building and manufacturing subsystems for the PTO, but this is a high degree of local content to fix the people and to transform the landscape to, for example, convert fishermen to technicians and convert old professions into the new professions that we need. We need now sea and land electrical engineers, sea and land mechanical engineers, sea and land control engineers, and artificial intelligence and programmers also. The machine is completely filled up with artificial intelligence, It can look 5 seconds into the future and predict what's going to happen in the next 5 seconds. So it's full. It's not only electrical and mechanical. It's full of machine learning capabilities and also artificial intelligence. So there's and software everywhere, as you can imagine. So it's not industry that will be just welding, cutting, and welding. Okay, there's jobs for everybody, sea and land.
Miguel, please, can you conclude?
Yeah, so just because this is floating wind, let's compare a little bit. And we actually need only 1/3 of the space for the same thing. That's very interesting summary. Yeah, so from the shore, you know that after 4 kilometers, you don't see anything because of the curvature of our planet. Here it's a little bit higher, and the visual impact is quite small. And you know the potential. It's like 500 gigawatts that are there, and we are not doing anything to get them. And Corpower is trying to tap into that amount of energy. Yeah, just to finalize, as you can see, the message that I just tried to send earlier on the variability of the profiles, you can see that line is our wave energy profile coming out from what we have studied in California. So the data is coming from California, and that's 1 week of production. So what we offer to the mix is a base load profile that can be used by the promoters to get a more stable profile while negotiating with who is going to buy the power. Okay, so reduce the variability effect on their approach to the market and to have a stable and more value-added profile. So this is one of the keys. And the next is just look at the ocean as a big battery and don't do overcapacity and overstorage. Just look at that battery and help us tap into that huge resource that's available there, because there's always waves and night and day. So this is it.
Thank you.